Howdy, today on Flipping Science we'll look at scum and chlorination. So science understanding we're going to look at. Hard water contains high concentrations of calcium and magnesium ions. Hard water renders soaps less effective and causes build-ups of precipitates. Natural modified zeolites can be used in the purification and softening of water through the exchange of cations, so explain how zeolites are used in water softeners. Then we're going to look at chlorination, so hypochlorous acid, chlorine and hypochlorates are oxidizers used for water disinfection. Explain the effect of pH on the equilibrium between chlorine and water, and hydrochloric acid and hypochlorous acid. So let's talk about scum. So soaps, as we have looked at before, they're long-chain carboxylate anions. When they're in water, they're normally sodium salts. The sodium detaches and you get left with a full negative charge at the end of the soap molecule. And this is what makes the soap effective. That makes it this end readily soluble in water, and the long chain on the other end is not soluble in water, at least to its ability to form micelles. Hard water contains high concentrations of calcium and magnesium. Calcium and magnesium ions, due to their strong charge, can stick to the soap anions and form these insoluble complexes that we call scum. The problem with this scum is it removes the soap from the solution, which means the soap can't do its job anymore. If it's trying to clean your clothes, for example, or your dishes, it comes out as scum, then there's a lower concentration of soap available to do the job. The other thing is, since it's insoluble, it settles down on surfaces. So it could settle down on your clothes, it could settle down on your dishes. Here's a shower screen, for example. We can see the scum, that white precipitate there. So hard water reacts with soap to form insoluble complexes called scum, and that reduces the effectiveness of the soap. So if we want to prevent this from happening, we need to get rid of the hard water cations. And we do that by softening water, and we can use ion exchange resins or zeolites to do that. Now, if you go interstate and you have a bath, you might notice that you get a lot more bubbles for the same amount of bubble bath compared to what you would get in South Australia. And the reason for that is South Australia has reasonably hard water. So we don't form huge amounts of bubbles, which requires micelle formation, because the hard water ions are reacting with the soap, and that's reducing its ability to bubble. So one of the problems with hard water is that it can form insoluble salts when it's heated. Hydrogen carbonate ions are present in water. If you heat the hydrogen carbonate ions with the calcium ions, you get insoluble calcium carbonate being produced, as well as carbon dioxide and water. This is called scale. It's an insoluble calcium salt. There's equivalent ones with magnesium as well. As it forms, it can cause damage to appliances. So here's a pipe, and we can see the scale deposit inside. That's reducing the ability of water to flow through. Over here and down here, this is an element from a heating apparatus for water. This too here, this is a boiler, so for people who are heating up their water. The scale that forms on the elements can reduce the efficiency of the element, meaning that more electricity has to pass through in order to heat it up. So if you can remove 321, so if you can remove those calcium and magnesium ions, it can reduce the scale deposit, and that can be beneficial as well. So as we said, hard water contains high concentrations of calcium and magnesium ions. One way of getting rid of them is by using zeolites. So zeolites are either synthetic or naturally occurring hydrated aluminosilicates with symmetrically stacked aluminium oxide and silicon dioxide tetrahedra. What that means is they have this shape. This shape has big holes in it, so it's very, very porous. And on the inside of those pores, there's a negative surface charge. We can make zeolites, and we can change the size of the tunnels or pores depending on what structure that we use. The way that we can use these to soften water is that we can stick positive charges of our choice on the negative surface of the zeolite. Then we can exchange those ions with the hard water ions to soften the water. And this is how a water softener works. So you have these beads of ion exchange material, that can be your zeolite, that has a surface negative charge, and we can charge it with sodium ions. So sodium ions don't affect soap, they don't cause build-ups of scale, so it doesn't matter if there's sodium in water, depending on the concentration that is. So if we have a look at this diagram here, we've got the ion exchange material, and we have magnesium ions are squares, calcium ions are triangles, and our small circles there are sodium ions. So the ion exchange material is originally charged with sodium ions. As the hard water passes through, the calcium and magnesium ions exchange places on the surface of the ion exchange resin, and they release sodium ions into the water. What that means is the calcium and magnesium ions are now stuck to the ion exchange resin, and they're not going to be present in the water coming out of the water softener. So here's another picture of the zeolite, and we can see the sodium ions stuck to the negative surface of the pore. And another diagram showing that originally we've got our ion exchange resin, our zeolite with the sodium ions attached to it. As the hard water passes through, the sodium ions get exchanged with calcium and magnesium ions, so the calcium and magnesium ions are stuck to the zeolite, and the sodium ions go into the treated water. So the water that's coming out has far fewer calcium and magnesium ions than the water that entered. So that's why we call it softening, because the water up here is hard, the water down here is soft. So this equilibrium here is set up where we have the sodium on the zeolite. We pass through the hard water with the calcium or magnesium ions, that's what the M stands for. Sodium ions go into solution, and the hard water ions stick to the zeolite. So the water passing through has higher concentrations of sodium ions, but it has lower concentrations of the calcium and magnesium ions. Now, it wouldn't be very good for the environment if this was a one-time thing. So what we can do is we can regenerate the zeolite. We recharge it, it's called. The way you do that is you pass through salty water back through your zeolite bed. So down here we have a brine tank. So this contains high concentrations of sodium ions. We pump that back over the ion exchange resin, the zeolite, and we get the sodium ions sticking back onto the resin. What that means is then the calcium magnesium ions will come back out, and we just discharge that water somewhere safe. So we're replacing the calcium magnesium ions with sodium ions, and then the zeolite is ready to go again. So now that we've looked at hard water, let's have a look at chlorination. The last step before water is distributed is that the water needs to be treated to kill off the bacteria that are present. Bacteria can cause a lot of diseases if they're present in water. So for large amounts of water, chlorine gas can be used. And when you add chlorine gas to water, you set up this equilibrium. So we've got chlorine gas and water, then we get hypochlorous acid, which is HOCl, hydronium ions and chloride ions being present. Now, this is very pH sensitive due to the fact that there's hydronium ions here. So you need to keep the pH at particular levels. Now, there's a few equilibria that are set up when you add chlorine to water, and depending on what type of chlorine you add to water, you get different equilibria. They're all sensitive to pH, so the water's pH is checked frequently to make sure that it's in the right ranges. Now, the best substance to have present in the water is the hypochlorous acid. It's a really strong oxidizing agent, which means it kills the bacteria readily, but it also doesn't have a charge. So because it doesn't have a charge, it passes easily through the cell membranes of bacteria. So it can go into the cells and it can cause oxidation of the proteins present, and that kills off the bacteria. Now, the hypochlorous acid that we added to the water, it partially ionizes the water because it's a weak acid. That produces hydronium ions and hypochlorite ions. Now, hypochlorite ions are also an oxidizing agent, and they can kill bacteria, as is chlorine. So chlorine gas can kill bacteria too. The most beneficial substance is the hypochlorous acid. And again, this is pH dependent. If it's too acidic, then we'll be too far in this direction. If the water's too acidic, it'll pass over here and it'll be too far in this direction. If it's too basic, we'll remove the hydronium ions, because the hydronium ions will react with the hydroxide ions, and we'll go back in this direction. So it has to be a balance in the pH in order to get the best oxidizing compounds in the right concentrations. Now, as I said before, the way that these things kill bacteria is by oxidizing the proteins inside. They have a strong oxidizing action. They cause the oxidation of the proteins inside the bacteria by themselves being reduced. That leads to cleaner water. Now, there's problems with using chlorine gas in that it is very toxic and it will kill you if you breathe it in. It's also very corrosive. So in small-scale situations, rather than using chlorine gas, salts can be used containing hypochlorite ions. So calcium hypochlorite here or sodium hypochlorite can be used instead. When we add these to water, we get another equilibrium being set up. So we have the hypochlorite ion in water producing hypochlorous acid and hydroxide ions. And again, we can see that this is going to be affected by pH due to the presence of hydroxide ions. If the solution is too acidic, we'll remove the hydroxide ions, then it'll force the equilibrium to the right-hand side. We might get too much hypochlorous acid present. If the solution is too basic, we'll force the equilibrium to the left over here, which will remove the hypochlorous acid. That will reduce its concentration, and we'll get too much of the hypochlorite ions being present. So again, we need to monitor the pH when we do this so that we make sure we have the right concentrations of each of the oxidizing substances. So here are the three equilibria that we looked at. The pH of drinking water is normally around about 7.5. And what happens at 7.5, if we look at our table here, is we get about 50% of our available chlorine as hypochlorite ions, and about 50% of it as hypochlorous acid. If we have a look at this graph over here, we can see where 7.5 is. It's kind of this nice middle ground where the water has a reasonable amount of hypochlorite ions from the sodium hypochlorite here, and it's also got a reasonable amount of hypochlorous acid. So it's a nice middle point. Questions you'll get on this, on these types of equilibria are determining what happens when you add an acid or a base to the system at equilibrium in terms of which direction the equilibrium will go. So let's have a look at a question like that now. So here's an example question. Sodium chloride is added to some swimming pools to reduce microbial growth in water. Electrolytic pool chlorinate is used to produce chlorine gas, which then reacts with water, setting up this equilibrium. Explain the effect that the addition of hydroxide ions to this solution would have on the equilibrium concentration of chlorine. So if we add hydroxide ions to this solution, on this side we've got two acids. We've got strong hydrochloric acid and weak hypochlorous acid. By adding the hydroxide ions, we're going to reduce the concentrations of these two since they're going to react with the hydroxide since they're both acids. So that's going to have the effect of pushing the equilibrium to the right-hand side, and that's going to reduce the concentration of chlorine present since that chlorine will react with water to produce more hypochlorous and hydrochloric acid. So by adding hydroxide ions, the equilibrium is going to shift to the right. That's going to remove chlorine gas and reduce its concentration at equilibrium. So today on Flipping Science, we looked at scum and chlorination. That's it for Flipping Science today. See ya.